Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I'm super happy to have Avrajit Bandyopadhyay with us today. Hey, Avrajit.
Hi, Professor Frank.
How are you today?
I'm doing good.
Where
Thank you.
are you located? Where's your geolocation?
So I am at Nainital. So it's a town maybe about 250 kilometers away from the national capital,
Ah,
and it's in the Himalayas. So it's high altitude.
oh,
With now it's very cold here.
what is your altitude where you're at? What
It's
is the
about six. It's about 2,000 meters.
Ooh, you are high. Okay, very cool.
Yeah.
Yeah, very nice, very nice. And what is your position there?
So I'm working as a postdoctoral fellow.
Ah,
In
you're a postdoc.
this is a yeah. So this is Aryabhatta Research Institute. So I
Okay.
finished my PhD last year and joined here as a postdoctoral fellow.
Well, congratulations, Dr.
Thank you.
Yay. That's awesome. Very cool. That's a pretty cool picture over your right shoulder there. Looks like, is that a picture of the moon?
So this one is the picture of Mars taken by
Mars.
surveyor.
Okay.
So this is the surface of the Mars, and the other one is the picture of the galaxy taken by the 3.6-meter telescope located here only in Nainital.
Ah, which galaxy is that, like M31?
So this is NGC 613.
Ah, okay. Mhm. Very cool. And we're going to talk about something a little different, I imagine.
Yeah.
But they're somewhere in between planets and galaxies. So that's where we're headed. So, Avrajit, what do you like to do for research?
So for my research, I usually work on the older population of stars, the ancient population of stars that populate our Milky Way halo, and also the stellar systems like globular clusters and satellite galaxies.
Mm-hmm.
So I try to look for the nucleosynthesis signatures of the early nucleosynthesis signatures and try to prove the nature and traces of the primordial population.
Very cool. Very cool. And in fact, that is going to lead us to this really lovely APJ article. Abundance analysis of new RPROS enhanced stars from the HESP-GOMPA Survey, HESP-GOMPA array. And Avrajit, take us away.
Yeah, thank you. So this article is based on the data from HESP. So HESP is the Hanley-Eschel spectrograph, which is commissioned on the 2-meter class Himalayan Chandra telescope. So fortunately for me, when I just began my doctoral studies at Indian Institute of Astrophysics,
Mm-hmm.
this high resolution spectrograph came up and it was commissioned close to the same period. So we started to work on this particular spectrograph and tried to do a survey, a high resolution spectroscopic survey of the metal poor stars in the galactic halo.
Mm-hmm.
So as an outcome of this survey, we got several interesting candidates, which included R-process enhanced stars and several other classes of metal poor stars. So we tried to discover the signatures of nucleosynthesis, the first generation of stars and subsequent evolution of the stars and the metals in them by this high resolution spectroscopic survey.
Okay.
So in this particular paper, we try to address the questions regarding the R process, the origin of R process, the nature of R process, the sites, the progenitor that could produce the R process in the early galaxy. So over the span of last 4 years, we have observed for more than 40 nights. So in
Wow.
India, the observation is based on PI system. Like there's no big groups or collaborations that do uh, have an allotted time for these observations. So
Uh-huh.
we have to, so the process is very competitive. We have to write proposals. And as expected, in high resolution spectrograph, it takes a lot of time to observe a single star.
Mm-hmm.
So we have observed roughly about 50 nights in the last 4 years and have finally did the analysis for more than 70 odd stars in the galactic halo in high resolution.
Okay.
So out of those, these 5 particular stars were found to be enhanced in our process. So this we was started in the late 2015 and went on till last year. So when we started the survey, there were hardly a handful of R process enhanced stars. Like we didn't have a large number. But now with this global effort of R process alliance that have come in, it's a wonderful, wonderful effort from their side, from the global initiative. the number has gone up by a large way. So initially we thought just discovering R process enhanced stars is good enough, but later on we have to change the subject, and then we went on to study the trends of different elements, the abundances, and try to find nature or any signature that can help us to probe this R process population.
Cool.
So the main question that we try to address is, apart from adding new stars to the known sample of our process enhanced stars, we also do roughly the statistics. And the main question we address is, the R process is completely something we really don't understand, like how the R process enhancement is completely decoupled from the hydrogen to zinc, and then the lighter and heavier neutron capture elements. So
Mhm.
how do they produce this excess of R process enhanced elements? We still don't understand. And again, uh, stars of metallicity -3, which contain the nucleosynthesis products of a single event, is so universal that it contains similar ratios, similar nature as we see in the sun. So
Mhm.
how do this universality or the robust nature of our process comes in? So what are the clues to them? So we try to address these questions in this paper. So we start with target selection. So for target selection, so HESP can operate up to a brightness of around 13 magnitude. So it's not very easy to find interesting candidates at such brightness. Like the
Okay.
HK survey of Beers and Hamburg ISO survey are done with most of the interesting candidates. So we tried to find some interesting low resolution survey, and we came up with this Marvel's pre-survey data. So SDSS is usually known for probing the fainter end of the stars, but the exoplanet survey of SDSS, known by Marvels, so there was a Marvels pre-survey that had this catalog of stars which are relatively brighter than the rest of the SDSS data. So we used the Marvels pre-survey to shortlist our candidates, and
Okay.
we went by the spectral fit. We chose the most metal poor stars in the Marvels pre-survey based on the spectral fit and the calcium K feature. Along with, we also looked for other signatures like carbon G band, like weaker signature of carbon G band, as most R process stars are known to be weaker in carbon if we don't consider the CMPR or CMPRS class. So we looked for those signatures, and then we shortlisted our candidates and went on with observations. And to build up a signal for each individual star, we observed them at a resolution of 30,000 as well as 60,000 for several exposures,
Okay.
because it was particularly difficult to obtain a good signal at the blue end of the spectra, which is the most critical for doing abundance studies of our process. Because most of the lines of N capture lies around the 4,000 angstrom region.
Okay.
And that's where the signal quality goes down in case of HESP. So it was a bit difficult to build up the signal. So it required several exposures.
One. Okay.
So if you look at the table, so for the analysis, we use the Atlas 9 models, like Kuruk's plane parallel atmospheres, and the turbo spectrum spectral synthesis code. And
Okay.
we use several techniques for finding the parameters, the stellar parameters of temperature, log G, and metallicity. In table, if you go to table 1, so yeah, so here we show the estimates for effective temperature, for example, for the different stars, using the different techniques that we have used, like H alpha from spectroscopy, and we also used the excitation equilibrium method using FE1 lines, as well as other photometric temperatures based on colors.
Mm-hmm.
And we also used Gaia and spectral energy distribution using VOSA.
Okay.
So also we used H beta. H beta is also somewhat dependent on surface gravity, like log of G. So we didn't include it in this table. So we carried out this process iteratively for effective temperature, log G, and metallicity until total convergence was reached. So finally, when all these methods converged to a single value, that was adopted as the effective temperature, log G, and metallicity, and that gave us the stellar parameters for the given star.
Okay.
So, so if you can show figure, figure 1.
Got it. Okay, figure 1. Let's blow that up a little bit. Okay.
Yeah, so here we show the synthesis for different abundances of carbon using the obtained stellar parameters. So red shows the best fit, whereas blue and black show the deviations by 0.2 dex. So this is one signature we use in the low resolution data to shortlist the candidates. And after obtaining the higher resolution using HESP, this is the carbon G band, and the spectrum was synthesized using turbo spectrum. And if you can classify, so if you want to classify, if you can show figure 2, there we synthesize the different elements like strontium, barium, and europium, which are the key elements for classifying the known R process candidates.
Okay.
So, yeah.
So it's the same cutting. Dots are the observations, red is a fit, and blue
Exactly.
black is plus minus half deck.
Yeah, plus minus half deck. And as you can see for the europium line, you can see there is a larger noise in the continuum.
Yes.
So this is what hampered us from doing a very good study for even the very small transitions. So we could not get a very good signal for the very small transitions, and that's what we want to focus. Like if we get a better signal to noise ratio in the blue region of the spectrum, we could do a much better job than what we could do using this telescope.
Okay.
So these are the three elements. Like europium is the tracer for pure R process. It's mostly synthesized via R process, whereas strontium and barium are indicators of S process. However, at the very metal poor end, it's not really clear how much S process contributes. S process usually contributes maybe from metallicity minus 2.6 to upwards, but the significance of the S process contribution is not very well tabulated at very low metallicity.
Right. Okay.
So these are the three elements we use for classifying our stars. And in table 2 and in table 3, we show the classification. Like, can we show table 2?
Table 3 we want?
Table 2 and table 3, yeah.
Table 3. Okay, there's our 5.
Yeah. So
okay.
this is. So in table 2, we show the observation parameters and the adopted stellar parameters, including the metallicity, which spans from minus 2.1 to minus 2.85.
Mm-hmm.
And in table 3, we show the abundance of the key elements that are used for classifying the R process enhanced population. Like we have carbon, we have barium, we have europium, and we have strontium. So out of this 5, 3 are found to be of R1 type, like moderately enhanced in R process elements, and 2 are found to be R2 type, which are largely enhanced in R process elements. And
when you
yeah.
do the fit, is that an LTE?
Yeah, that is an LTE.
It's an LTE fit. Okay.
Yeah.
Okay.
Yeah. So once we are done with the stellar parameters, we do the spectral fitting. We obtain the abundances for the different whatever elements we could find in the spectra, and then we also did a literature study to find the trends of the different known R process enhanced stars, starting with Berkeley in 2005. We also did literature survey of the unbiased studies, like studies which did not actually target the R process stars, starting from the famous McWilliam paper of 1998.
Yes.
And we also, we tried to probe the trends for the biased as well as unbiased studies of our process and try to find the different populations. So in figure 4, if you can go to figure 4.
Let's blow this one up. Okay. Figure 4. Bandwidth delay.
Yeah, so here we saw the distribution of europium over iron. So since we have already discussed that europium is the tracer for the pure R process, so that current nomenclature for classification of R process enhanced stars tells us that any star which has europium greater than +1 is classified as a R2 star. They are considered to be the most enriched in R process elements. Whereas stars within europium plus 0.3 to plus 0.1 are called R1 class, and anything less than that, but still showing a higher europium than the general halo stars, with a preferential production of lighter R process elements like strontium by barium greater than 0.5 are called the limited R, like but it seems that the R process production was limited in some sense. So you can see from this sample, like two of our stars, two of our new discoveries fall in the middle zone. We call them R1, and the two of our samples fall in the R2 class, which are shown in pink triangles, and our new discoveries are shown in red filled diamonds.
Okay.
Yeah, so we can move to figure 5.
Okay. Figure 5. All righty. Now we got barium.
Yeah. So again, now, so barium and europium are two of the heavier encaptured elements, but barium is maybe produced by S process, whereas europium is primarily produced by R process. In the solar metallicity, 85% of barium comes from S process, but following the similar 2004 calculations. And whereas at the very metal poor end, it may not be so, the contribution of R process may be significantly higher. So there we use the nomenclature of barium by europium less than minus 0.8 is considered as a pure R process origin. So there you can see most of the R process enhanced stars shown in the colored triangles like blue, black, and pink.
Okay.
They all fall in the region barium by europium less than 0. So europium is preferentially produced over barium. That is the main criteria that's used to trace the R process enhancement. But very few of them fall within like less than by like barium by europium less than minus 0.8. So the pure R process origin is considered for a very few of the stars, and from our sample, the 5 stars that we have got of R process enhancement, only one falls in this category, which falls below the barium by europium minus 0.8. So this dotted line shown in the solar R process, so any star falling below that line is considered to be a pure R process origin.
Okay.
So
let me ask a question in my what are the small open circles?
so these are normal halo stars,
Got it.
which may be the normal halo type or the CMPRS category, which shows the enhancement in carbon also.
Yes. Okay.
Yeah, so now if you can move to figure 6.
I certainly can. Figure 6, and we got a double wider here. Okay. Boom, bam. Nope. Okay.
Yeah, so now if we plot strontium over, so strontium is an indicator of the lighter R process, whereas barium and europium are indicators of heavier R process. So plotting the ratio of strontium and barium tells us the contribution, the relative contribution of lighter to heavier R process in comparison to europium over Fe. Here we can see clearly that the limited R stars shown in black fall to a completely different evolutionary scheme. They show a flat distribution, whereas the blue and the pink, which are the R1 and R2 stars, show rather a downward trend with respect to europium over Fe. So this indicates that the origin for the lighter R process, in this case shown by strontium, may be entirely different from that we get for heavier R process. Because as europium increases, strontium and barium goes down, implies barium also increases as europium increases, since in the earlier figure, figure 5, for barium by europium, we get a flat distribution for all the population. Whereas here, strontium by barium goes down as europium increases, implies barium increases at the same rate, whereas strontium stays constant. So the origin for strontium is not evolving at par with barium and europium. So this is something we want to focus, that the origin for the lighter elements may be completely decoupled from the heavier elements. Firstly, our process is completely itself decoupled from the origin of the Fe peak and the lighter elements. And again, in our process, we find the lighter peak is decoupled from the heavier peak. So similarly, if we remove the dependency on metallicity, we do the same plot, strontium by barium versus absolute abundance of europium, like europium by H. We find a similar trend, like lighter R process, like the limited R stars are decoupled. Now, in the right side panel of figure 6. Yes, in this panel, we do the absolute, the europium by H. We plot strontium by barium as a function of europium by H to remove the trends with metallicity. Here we find a similar distribution.
Okay. I missed the
So,
x-axis that changed there. Okay.
yeah. So
Okay.
next what we wanted to do is we wanted to look for the progenitor of this R process enhancement.
Mhm.
Like, what is the source of this R process? Is this collapses like neutron star merges? Or is there supernovae type 2? Or is it some events? So we will not go into the modeling aspect because that's something we have not done. So we use the observational signatures. Like magnesium is a tracer for core collapse supernovae type 2.
Okay.
So we have taken magnesium as an indicator of supernovae type 2 in figure 7, and we have used europium as a tracer for R process.
Okay.
We used this like limited R stars are shown in black filled circles, R1 are in blue, and R2 are in pink. So we find a small downward trend of magnesium versus europium. So
Uh-huh.
as europium increases, so as the R process enrichment goes up, we find the relative production of magnesium is going down. So the open circles you find here are taken from the unbiased studies like McWilliam, Carroll, 2004, like McWilliam 1998,
Yeah.
whereas the filled circles are focused R process studies. So, and both the studies tell us that there's a same, we see the same trend that as europium increases, magnesium goes down, indicating as we find more and more enrichment in our process, that the actual contribution from supernova is going down. So it's very unlikely that supernova can be the primary contributor to the R process nucleosynthesis, going by the downward trend. And in the right-hand side panel, we plot europium over Mg versus metallicity,
Yep.
and there, and we do not find a largely different distribution than what is expected. So it shows more of a, so R2 stars are expected are largely enhanced in europium over Mg, whereas the R1 and limited R goes to the bottom of the plot. And there is a significant scatter with lack of a proper trend. But in the left-hand side panel, we could clearly see that the downward trend indicates that contribution from supernovae goes down as the R process enrichment goes up.
Yep. Okay.
Okay, so next, if we come to figure 8.
Actinide boost. Okay, figure 8. Whoops, sorry about that, people. Blow that. Okay, figure 8.
Yeah, so here we try to find clues about the distribution of R process enhancement, the R process enhanced population in the galactic halo. So here again, we use strontium by barium versus barium over H. So strontium, so if we go by the approach taken by Sujimoto and Shigeyama in 2014 and 2015, they consider strontium to be a lighter element produced purely by supernovae, and barium as an indicator of heavier element that's coming from neutron star merger. So strontium by barium, so having a higher ratio of strontium by barium indicates that the contribution is largely from supernovae, whereas the lower values for strontium by barium indicates the contribution is largely from neutron star merger. So
Okay.
we have taken that in the y-axis, and in the x-axis we plot barium over H. And we use the same symbols, like blue is for R1 stars, pink triangles is for R2 stars, and black filled circles are for limited R. So here we find that the blue and the black show show a linear trend with respect to barium by age, whereas the pink triangles, which are the R2 stars, show a rather vertical distribution and also spans a lower range in the barium by age. So this indicates the blue and the black, which are the limited R and the R1 stars, may show a gradual evolutionary development of R process, whereas in R2 stars, or the most enhanced R process enhanced stars, it's more episodic, or maybe probably an episode or maybe a few disentangled episodes have contributed to the formation of this R2 class, whereas R1 and limited R show a gradual evolutionary diluted R process enhancement. Similarly, the halo stars do not show such periodic, like episodic enrichment of R process enhancement. So here we find stark difference in the evolution of the R process enhanced stars for the R2 class and the R1 and limited R category.
Okay, I'm with you.
Yeah, so now if you can come to figure 9.
Okay.
So in figure 9, we show the universality of the main R process, like the starting from the peak at barium up to diasporium. So we could measure all these elements in these stars, and our stars fall within show the expected universality of R process, whereas we find significant dispersion at the lower end, like strontium, yttrium, zirconium. The first R process peak show a large scatter and the expected dispersion deviating from the universality.
Yep.
Again, for one of the stars, you see at the heavier end of the R process at the thorium. So at the atomic number 92, 91, so there also we could find thorium. So thorium is slightly enhanced from the expected universality, expected production of R process. So this brings us to the case of actinide boost. So note that R process contains different sites, like the R process is disentangled from the main production of hydrogen to zinc. Then lower R process has a different progenitor, has a different site from the main R process. But even at the heavier end of the main R process, there must be variation within. So even like peaks like thorium and uranium show either actinide boost or deficiency in actinide elements. So if you can come to figure 10.
Okay. All right. I'm good so far. Okay. Okay.
Yeah. So here we try to use thorium as an indicator of age, and we include in this all the previous studies that have detected thorium along with europium as function of metallicity to determine the age. But unfortunately, like this feature of actinide burst leads us to unphysical ages. We get a negative age that is not physical. So for this, we require maybe other actinide elements like uranium. So sadly, unfortunately, we could not detect uranium using our spectra.
Yeah.
So we hope to do this using a larger telescope with a better signal to noise, so that we can find the cosmochronometric age using these two indicators. So this actinide burst, so this event of actinide burst tells us that there can be a single progenitor that is producing R process, but even if there is a single progenitor for the main R process, there must be variations within that single class.
Right, and then we have a new object on here, reticulum 2, ret 2.
Yeah. So reticulum 2 is another galaxy that we really don't understand. Like it shows large enhancements in R process for majority of their population. So was this polluted by a single event in the galaxy, or did they just migrate from, or we don't really understand.
Right. Yep. Okay. Very good. So what do we get out of What are some of the conclusions coming out of this work?
So one thing is we need to provide, so we don't really understand our process. We don't really understand the origin of our process. So we depend on the theoretical calculations or the simulations to understand what can be the origin of our process. For that, we need statistically significant number of stars. So when we started this project in 2015, end of 2016, so we hardly had about maybe 5 or 6 stars with that R2 category, like large enhancement of our process. Now with the advent of our process alliance and some other efforts globally, that number has gone up to 20, but it's still not very significant. So we look forward to adding adding a significant number of stars. So in this study, we have added 5 stars of our process enhanced category to the known existing literature. And we hope this will be taken up again to observe at high resolution, at better signal to noise, to obtain a better nucleosynthesis pattern. And this will be used by the theoretical calculations and modelers to better model the supernovae or the collapses or neutron star black hole merger, so that we can understand. So unless we have a large number of stars, we cannot really understand what exactly is happening, or how much is a scatter, or what is a dispersion. We also probe the different classes of our process enhanced stars, and we find the R1 and the limited R show a different evolutionary trend in comparison to R2. We also note that the contribution of supernovae goes down as the contribution of our process goes up. So our process is not directly correlating with the supernovae contribution. So these are what we try to focus in this paper.
Cool. So let me ask, since you hit upon it, so this study increased the global supply of these stars by what, 20%, from 20 to 25 or so?
Well, it was supposed to when we started, but now there's more like a data explosion with so many new stars coming up. But still, it's a significant contribution, I believe, in this field of galactic archaeology.
Is there stuff coming in the future? So what do you think, what are the next steps? Where do we go from here, given what you've published? Are there new surveys coming up that could increase the sample size of these stars to 1,000,
exactly,
to 100, to
a
million?
So maybe the very R process enhanced category, maybe 100 in the next 5 years. We can hope to reach 100 in the next 5 years, because the large surveys that are coming up, like Foremost is coming up, Moons is coming up, and Weave is coming up, and Gala is already working. So these surveys are expected to raise the number of R process stars, and R process alliance is the global effort that is bringing up so many stars in the last few years. So we expect the number to go up, and we expect the models to get better, and we expect to have a better understanding of our process in the next 10 years. We really know, so that we can really know where this our process is coming from and what is really so strange about them.
Indeed. Yeah. The origin of our process is certainly a hot topic from many regards. Definitely observational, theoretical, individual events, neutron star mergers, or collapse. So it's a happening topic. There's going to be a lot of action in this over the next 5-10 years, I think, or so. All righty, Avrajit, I want to thank you so much for spending some time today on your morning.
Yeah, thank you for having me.
For your paper. No, you're welcome. My pleasure. I think it's a really lovely paper. I think it's very nice. It was great that you were able to walk us through it.
Thank you so much.
All righty. Thank you, everyone. And we will see you on the next one. Bye-bye.
Bye.